So welcome to the second day of the 2025 Nobel Lecture Series featuring speaker Dr. David Tarasick from Environment and Climate Change Canada. Today's talk focuses on the methods used to make ozone measurements, a field to which Dr. Tarasick has made many contributions. These include creating the Canadian operational procedure for forecasting total ozone and UV radiation in ECCC, examining instrument measurements in lab and chamber conditions, and using them to calibrate measurements from Canadian ozone zone network in the field. These works significantly improve the measurements from the global network of ozone measurements. And before starting the talk, there is two unofficial information I need to bring. One is from the building management that we need to ensure to bring out any consumable carbohydrates and their containers that we bring into this room out with us. And also from the organizing committee that we also invite students and postdocs who are interested in Dr. Tarasick's work to join us in a pub night event today at 6 p.m. at the Prenup Pub down at College for some informal chat with our speaker. With that being said, now let's welcome Dr. David Tarasick to share his story on measuring ozones.
Thank you. Well, good morning. Today, am I on? Yeah. Okay. Today, I'd like to talk to you for a bit about ozone measurements, a bit from the past, not so much as yesterday, but and also from the present, and maybe even a touch about the future. So, tried to illustrate in this title slide some of the types of methods that have been used. You can see an ozone sonde up here. That's an old, now really obsolete Brewer mast instrument invented by Alan Brewer, who, as many of you will know, was a professor here until 1977. So he's very instrumental in the field. And he developed the first ozone sonde running on the chemical method, potassium iodide. This picture from about 100 years ago, I've used many times before. It's rather nice. And it shows, I believe this is Henri Buisson's assistant with an instrument measuring total ozone. There's a mirror here that's pointed out the window, prism, I think, actually. And so clearly they're pointing at the sun and making a measurement of the total amount of ozone between the instrument, or the Earth, and the sun. And then, of course, as I mentioned yesterday, for the first 10 years or so, all of the scientific papers on ozone talked about how it smelled, because that was the most sensitive instrument anyone had for detecting ozone. And so I put a picture of Schoenbein there. To point it this way. All right, how about this? Okay, there we go. All right. So ozone, as I mentioned briefly yesterday, is a very reactive gas. It also has strong absorption bands in the ultraviolet, but also in the visible and in the infrared. So there have been many methods developed to measure it over the years, some of them going back, as you can see, almost 200 years. Some of them much more recent. LiDAR really wasn't possible until the invention of the laser and the modern computer, because many of these more modern methods involve quite extensive data reduction. So the first one that needs to be mentioned, of course, is total ozone measurements. The picture at the top is the Dobson spectrophotometer. developed in the 1920s and 30s by Dobson at the University of Oxford. It's a manual instrument, so the data reduction was very simple. The instruments below were developed actually to a large extent here at the University of Toronto under Brewer, and then later at Environment Canada when Brewer's group founded the ozone program at Environment Canada. And so these instruments here, these Brewer instruments, are on top of the building where until recently I worked, and that is the triad. The idea of the triad is that those instruments are continually compared with one another. So you have a stable reference. If somebody's up on the roof and he trips over one of these instruments and doesn't tell anybody, you can see the change in the data. You know something's happened, you know it needs to be calibrated. So this has been essentially replaced by a more triad of more sophisticated instruments called double Brewers. And there's also another triad for the UV measurements. It's kind of expanded quite a bit. We have about 14 of them on the roof now, I think, including the traveling standards that are used around the world to calibrate them. But both types of instruments are used in the global network still, the manual one and the Brewer one. So the Dobson uses pairs of wavelengths in the ultraviolet. You'll remember the spectrum from yesterday. Remember that this is a logarithmic scale, so this is a factor of, this is 4 orders of magnitude here, factor of 10,000. So there's actually an order of magnitude in absorption between this wavelength and that wavelength. The Brewer takes measurements, precise measurements of ultraviolet radiation at 5 wavelengths and uses those to analyze the amount of ozone in the column. So it's using more than just a pair of wavelengths. And that required a primitive computer at the time that the Brewer was designed. It now uses a PC, of course, but and just to reiterate what I said yesterday, this is the solar spectrum measured above the atmosphere. This is a measurement of the UV spectrum from Brewer instruments. Actually, there's 2 there right on top of one another, different days, very similar. You can see that ozone is taking virtually all of the short ultraviolet radiation out of the spectrum, and by extension, you can see that if you were in space for a few seconds, you would get a terrible sunburn. So, other instruments, this is a much more recent one, the Pandora. Some of you will be familiar with it. It's a diode array spectrometer. It measures the entire UV visible spectrum simultaneously, and there's a lot of sophisticated algorithm work to untangle that and do the spectral fitting that's required to retrieve ozone. And because it's also measuring in the visible, it can retrieve several other species which have spectral signatures in the visible. The Pandora can also be used to, oops, didn't mean to do that. Yeah, let's go this way. Can also be used to make measurements at different angles, so you can get some profile information. It's fairly limited, and it really only works for NO2. Ozone there have been a lot of attempts to get some ozone profile information in the troposphere out of that, but it hasn't really worked so far. That's perhaps something for the future. It's the notion is simply that you're going to see something different depending on what angle you're going through the atmosphere. And so if you can estimate your scattering height, which is what this is showing here, you can get crude profile information. It's usually about maximum of 2 pieces of independent information. Okay. Now, much closer to my heart is this little device, invented by another Canadian, actually, although he went to Boulder before he published his work, so the Americans tend to claim credit. But he was actually, Walter Comer was a Canadian, and he worked at what was then the Meteorological Service of Canada. So this theme was going to run through my talk. Canadians did basically everything. Not me, but other Canadians. Anyway, this uses this potassium iodide reaction, which goes back to 1845. Looks very straightforward and simple. And as a physicist, I first looked at this and said, wow, that's really great. We get 2 electrons for every ozone molecule, dead simple, should be an absolute measuring device. Well, that's what a physicist would think. Turns out it's not quite that simple. You get approximately 2 electrons for each ozone molecule. Depending on losses, depending on side reactions, there's a buffer in the solution because the stoichiometry, 1-to-1 stoichiometry only works at around pH of 7, but then you can get side reactions with the buffer. And anyway, the whole thing's kind of a mess, which makes it very interesting for scientists, of course, to try and untangle that mess. So we have done a lot of work on this recently. For a long time, potassium iodide methods were the method of choice for surface measurements, which was mostly what people were doing other than measuring total ozone. Spectroscopic measurements were extremely difficult, so there's only a few from the 1930s and 40s, but there's lots of instruments being developed that use this potassium iodide reaction. Many of them gave funny results. Going through the older literature, you find results that make no sense, frankly. Some you can just throw out as absurd. Others that, well, Duvalier, oh, sorry, I've gone forward again. Others that have give inexplicably high values. Duvalier's paper from 1934, we scratched our heads about for ages because it's very clear that the crazy measurements he got, he understood didn't make any sense. And he went through his whole instrument setup meticulously to try and understand what was happening. And he ended up concluding that the stratosphere had just come down to the surface and sat there for a while. And we've never seen anything quite like that since. But if I dig into the records, our Canadian records, I do find a few instances, not as high as his, but a few instances where we did apparently measure extremely high ozone. So we ended up putting a question mark beside that, not throwing it out. Anyway, by the 1980s, when benchtop UV analyzers became available, ones that actually didn't need to be calibrated. The original ones needed to be calibrated to potassium iodide, so they weren't any help really. But once they became stable enough to be independently calibrated or hold their own calibration, the potassium iodide method was largely abandoned, except for ozone sondes. And for more than 50 years, people have been trying to develop a better ozone sonde, and they've not succeeded. And so a few years ago, I guess a few decades ago really, showing my age, it was about 20 years ago, we really started trying to improve these measurements to understand them better. And I think we've improved them by about a factor of 2. Ozone sondes used to measure in the 10 to 20% uncertainty range. We've got that down to around 5%. And this is from a paper, fairly recent analysis of an error analysis or uncertainty analysis for our station at Edmonton this year. already alluded to these surface analyzers, which completely took over from potassium iodide-based analyzers once they, around late 1970s, they become stable and independently calibrated. They have two chambers, and they continually switch between the chambers. One of them has an ozone scrubber, takes out all the ozone, and you look, it uses a very strong line from a mercury lamp, one that's strongly absorbed by ozone in the, right around, I think that's what that's showing here, around there. And so you have a differential absorption measurement, and you swap chambers just in case of contamination, so that can be taken out of the system. There are a variety of models, but this one made by Thermoelectric Instruments is probably the most common. You'll also have heard of the CIBI instrument. That was the first one to be recognized as a standard instrument, and they're used a lot too. Okay. You have one of these instruments, at least one here at U of T, I think, an Fourier transform interferometer. You can also get, oh, sorry, I'm on LiDAR, pardon me, skipping word. We also have laser-based instruments using an ultraviolet laser with a pulsed beam, which allows you by very precise timing to tell where the absorption from your backscattered signal is coming from. You can get altitude information. Depending on the wavelength you choose for your laser, you can either measure in the stratosphere or down in the troposphere. Shorter wavelengths in the UV will be more strongly absorbed, so they won't reach much above 15 kilometers. So they're both stratospheric LiDARs and tropospheric LiDARs. They also use the principle of differential absorption, and these could not exist without modern computing because the data reduction is extremely complex. You have to worry about aerosols, you have to worry about timing, you have to worry about your wavelength shapes and shifts and all kinds of things that probably I shouldn't talk about because I'll get myself into trouble. This is a schematic of I think it's the stratospheric dial we have at Eureka. I'm looking for confirmation to some of my colleagues because I've never seen it. Okay. All right. Yes. Now FTIR. We have a few of these instruments in Canada. There was talk about a network a number of years ago, but we've got, I think, only, I don't know, how many do we have, Kim? 2 or 3? 3? There's one at Eureka, right? Yeah. Does it not be? Oh, is it? But it is still being used. Is Richard still running that? Yeah. Okay. So, because of the very precise spectral nature of an FTIR, you can do a lot with different wavelength bands, and that's what this is attempting to illustrate here. Is what we call the averaging kernels, and that for the data inversion, the data reduction, that and these different bands, spectral bands, are more sensitive to certain altitudes of the ozone distribution than others. This one here gives us some information in the troposphere, as you can see. And this one is sort of lower stratosphere around the tropopause, and so on and so forth. So there's a process where you iterate towards a solution. It's, again, computationally quite intensive, but you can get some good information about the troposphere, about 1 degree of freedom there, meaning one piece of independent information. So when I talk about independent information, I mean you can get a measurement for the amount of ozone in the troposphere that with one piece of information. If you have two, you can separate upper and lower stratosphere or troposphere and so on. So there's several pieces of information in the stratosphere where most of the ozone is, and generally around one in the troposphere. And this was an error analysis on the side there. Okay. I can't go by without mentioning MANTRA, which Professor Strong ran back in the early 2000s. We flew a whole lot of instruments on a large balloon, measuring a variety of different things. They are aimed at nitrogen in the atmosphere, but we also measured ozone profiles. I was involved with making precise measurements of the UV spectrum and detection of chlorine monoxide. Very complicated affair with, I guess, years of preparation. And but we did get some good results on at least one of the flights, and we had an interesting time with some of the other ones. You can ask questions at the pub night about those. I won't tell those stories right here now. And this, I want to emphasize this because this is brand new. For years, literally decades actually, myself, some of my colleagues, other colleagues also tried to get Canada to be part of this commercial aircraft system. It started in about 1994, I think, it's the first data, with it was a European project. Essentially, you take one seat out of the aircraft, you put a rack of instruments in, and you can measure whatever you can measure through a hole in the side of the aircraft. Getting a hole in the side of the aircraft was the big part, because to get an aircraft recertified after you put a hole in the side is a huge deal. And we were told over and over again, forget it. There's no way, that's at least $1 million. And we would say, but these aircraft, it's the same Airbus that is landing, and they're even, if they're flown by Air France or Lufthansa, they're landing in Toronto. So why? No, it doesn't work that way. We have to redo this. NAV Canada had to redo the certification. I sent messages up through senior management talking about how important, how valuable these data were, and they're cheap. I mean, that rack of instruments costs, it's maybe a one-time investment of $50,000, which just one. And then you get the data every flight, every time they land, every time they take off, you get a profile. So imagine my astonishment when one day I got a call from my colleagues in France and said, hey, Air Canada is putting one of our instruments, one of our packages on, and are you interested? Am I interested? I've been 15 years, I've been sending notes up the chain, senior, we should do this, right? $50,000. It's one ozone sound station costs that much to set up. And anyway. Environment Canada, yeah, it's government, what can you say? Anyway, we now have an Air Canada jet that has one of these packages. It's measuring ozone, it's measuring carbon monoxide with every landing and every takeoff. I was telling Professor Jones that we actually have profiles from those wildfires in 2023 because they started just before the Calgary wildfires. So I've seen profiles from Calgary from the first part of this program. So here's a suggestion. The data's out there. As far as I know, nobody's using it yet. It's a gold mine. But there's an example of a few of the profiles from cities. because these aircraft are flying all over. And it's not just the Air Canada ones. I mean, there's about 20 now in the IARGUS fleet. So the foreign aircraft that are landing in Halifax and Toronto, they also give us profiles. The ones that have those packages. There are about 20 aircraft in the fleet now that carry these packages. Okay. Satellites. Not everybody knows satellites measure ozone. In fact, we have a lot of them right now because they were all intended to work typically for a two-year lifetime. The usual design planning is 2 years, sometimes 5, but usually it's around 2 years. And many of them have been operating for close to 20 years. So we actually have quite a number of instruments that are measuring total ozone, which is good because they do a good job of that from above. Most of the ozone being in the stratosphere, that's a relatively easy measurement to make. You're guessing a bit about the lower atmosphere, the troposphere, but these are a pretty solid measurement, and they claim stability close to that of the Brewer. I think I said the Brewer was getting around 1%, which is pretty darn good for measurements of any sort, let alone the atmosphere. These are also claiming stability of close to 1%, under ideal conditions, of course. Somehow when you look at the data, it's never quite as good as the originators like to claim. But another type of instrument, which many of you will be familiar with, is the limb sounder. So instead of looking straight down, these look sideways at the atmosphere. And so you get profile information. Some of them use passive radiation from the atmosphere. Ones like ACE on SciSat use solar occultation. So they observe as the sun sets and rises through the atmosphere. They only get about 30 profiles per day, but they're highly accurate and they're self-calibrating because you're always seeing the sun above the atmosphere, and then as it dips down through it or comes back up on the other side, you get a highly accurate method, a highly accurate measurement of the profile. Still with a lot of deconvolution because, of course, at every layer of the atmosphere, you're looking through, except at the very, very top, you're looking through several layers of the atmosphere. So there is a lot of work for IT specialists. Now, if you combine those measurements, you can get with some fair bit of data massaging, you can get a rather decent measurement of ozone in the troposphere. The entire amount, you don't get more than 1 degree of freedom generally with this method, but you do get something like this. These are Jerry Zimke's reductions from oral MLS and OMI. They're also available on, he puts them out on the internet on a monthly basis, so you can use those if you have a use for them. And that's one method which is used by a number of different people, a number of different products. It's also possible to use spectral information, more spectral information, like I mentioned with the Fourier transform interferometers. You can look at different bands that are sensitive or more sensitive to different regions of the atmosphere, different altitudes, and get height information that way, separate the profile. It's an approximate method, but it also works quite well. And this is an example from GOM. And this was an attempt I did in a paper a few years ago to try and bring all of that together. I'd look at the quality of of the tropospheric product. And there are many tropospheric products. I think there's something like 16 in that list. And what I did was I looked at all the comparisons with, as it turned out, ozone sondes. That's all anybody compared with, which is a surprise even to me. But it appears that when we weren't really paying attention, ozone sondes have become the gold standard for measurement in the atmosphere. So all of these are compared to ozone sondes, which of course is in situ measurements are really what you want to look at when you're trying to see if your profile is any good. And what's clear from this is that while the biases have gotten better, especially in recent decades, the uncertainties, and these error bars, those are not 95%. Those are not 2 sigma. They're 1 sigma. Okay, that's just one standard deviation on the measurement. So the individual errors are pretty horrible. So there's a lot of uncertainty there. Well, if you don't have a satellite, the other way to get a global picture is with a network, which is why Dobson started the first ozone network in 1924, I think, somewhere around there. And there were more instruments built, especially once this instrument, this more modern version of his spectrometer, started to be produced. But it really got going in the International Geophysical Year in 1957. And a lot of our measurements in Canada go back to 1957. Now, now you have quite some 400 stations in the World Ozone Data Center that are reporting data from various methods. This picture is a few years old, but you can get a similar picture by going on the website. And this was a very important effort under the auspices of the WMO, World Meteorological Organization, to bring all of this data together so it was accessible to all researchers, so that we're all sharing data. And and back to ozone sondes. These are similar maps before 1990 and after more recently after 1990. I talked a little bit before about some of the earlier measurements. There were a lot of different methods that were used early on, but first real networks were with electrochemical sondes. There were a variety of types of electrochemical sondes. They all used the potassium iodide reaction, but they had different construction, and so they had different losses and different amounts of interference and all those things I alluded to that make it so complicated and interesting. But it has turned out that the one type of sonde has become prevalent, and that's why you see all these circles here in the more recent data. Virtually everyone is flying ECC sondes, and there are about 60 sites globally now, making profile measurements typically about once a week. It's not very often, but it is a bit expensive. Each profile costs $1,000 roughly. So oh, yeah. So I think I already said some of this. Regular ozone measurements start in the International Geophysical Year. But just for fun, I also wanted to mention that the first ozone network in Canada and perhaps in North America, there was one in Alabama about the same time, but they're within months of each other, was set up in southern Ontario. And the issue was tobacco fleck. The very important tobacco crop in southern Ontario was threatened because of this damage to tobacco leaves. which they suspected was due to ozone. And indeed it was. And so you have these papers from the 1960s and 70s discussing this very important problem. Now, as you know, it's not an important problem anymore. Nobody cares, but at least about tobacco damage to crops. But it is still important to other crops, especially wheat. And there's another area where nobody's doing any research these days. So anybody who's looking for a research topic, I have lots of ideas. Okay. We have quite an extensive network in Canada. And I've indicated by little symbols, the Brewer instruments, that's the little red boxes there, the ozone sondes, and a couple of LIDARs. A very nice automated LIDAR system that was developed for tropospheric measurements at Environment Canada that is sadly not being used at the moment because the fellow who developed it retired and nobody's taken it over. But it was the most advanced setup in the world. Still is, I think. I showed this slide yesterday. The other one was a little less busy, but this one includes all of the surface monitors. There are a couple of hundred surface monitors, mostly in urban locations. Yeah. Mm-hmm. So that's what it looks like, and I think quite importantly, there was a project a few years ago to try and collect all of this data and bring it together in a way that was more accessible to researchers. The World Ozone Data Center that I talked about before has focused on stratospheric ozone, and so it tends to have total ozone measurements and ozone sonde measurements. TOR was all about getting the surface measurements together. And there's a lovely website where you can download data and you can find out profiles from from individual stations. I mentioned the aircraft, the commercial aircraft, Mosaic, Iagos, it's now they land at airports all over the world. So effectively, it's a global network. There are also smaller networks of other methods. Fourier transform interferometers, there's a few LIDARs around the world, and the squares indicate a profiling method that's done with primarily the Dobson instruments. But ozone records don't all agree. So one of the problems you run into when you have all these network measurements is you end up comparing them and you go, don't get quite the same thing. So you need to sort out the differences. It's an opportunity, but it's also an obligation. This is showing some of the differences from one of the recent ozone assessment of ozone depletion that they're mandated quadrennially by the Montreal Protocol. And you can see that the differences there really exceed the uncertainties. And such uncertainties impede the detection of reliable trends. You need to know to what extent your satellites are drifting. And that's what this is, comparison with LIDAR, comparison with ozone sondes, attempting to measure how much satellite instruments are changing in the space environment. I'm trying to get all these differences down to where you can actually see a reliable trend. So we've done a lot of work in trying to improve ozone sonde accuracy because it's a two-way street. We're trying to improve the satellites, but we need to know how good the ozone sondes are. And we need to know how steady they are because they're critical for combining satellite records. A lot of satellite records, well, they're 5, 10 years, sometimes 20 years long, but eventually they end. Your instrument stops working. And you need now to stitch together that record with the record from a subsequent satellite. And there are always unfortunate differences. So there's been intercomparison work with ozone sondes pretty much since the beginning of the ozone sonde record. The first one was only 4 years after our station Resolute started. And more recently, we've done them in a chamber facility in Ulick, which is unique in the world. And that's led to a lot of understanding about how the instruments work. And don't think I have time to go into this in detail, but I mentioned side reactions. There are slow time constants which seem to be related to the production of hydrogen peroxide through a side reaction, which is kind of amusing because that's what Schoenbein called ant-ozone. So in a way, ant-ozone is messing us up in the, especially in the troposphere, where we have, where it matters quite a lot in the upper troposphere where ozone concentrations are low. And so we've also discovered that with the changes in sonde type, there are differences because there are quite a number of different electrochemical sondes in the past. Now everybody's using ECC sondes, electrochemical concentration cells. And there have been gradual changes in procedures that have made a difference. However, and this is one reason why everybody switched to these sondes, is it looks like the ECCs are very stable with time. So that's very encouraging. And also, most of this difference is in the troposphere. Sondes, of course, when the sondes were invented, nobody was interested in the troposphere. They wanted to know about the stratosphere. And so the troposphere is kind of an add-on. But they do give accurate measurements if they're properly, calibrated. This is from the long-term comparisons with total ozone measurements. We can say with a fair degree of certainty that there hasn't been a lot of change in the stratospheric measurements. So most of this change is in the troposphere. So that's good news overall. The same program, the same assessment that happened a few years ago compared the other methods. And actually, we came out with the happy conclusion that they all pretty much agree within their uncertainties. It looks like the ozone sondes are a bit high in the troposphere, but if you allow that, then everything kind of makes sense. I mentioned that satellite biases are large and satellite uncertainties are quite large, so there's an area for it. Other important applications of all these methods. There are different ways of measurement that can give you more different or more information. One, quite obviously, that you've all, I'm sure, have heard of, aircraft campaigns, where you have a multi-instrumented aircraft, research aircraft, rather like the balloon campaign. These are tropospheric based. And this is just one example from a project a few years ago. We had an extensive field study as well to support it. And we actually had a strategic network. Ann Thompson, who's the Nobel lecturer about a decade ago, talked a lot about this because this came out of our first IONS project, where we contributed some sondes from Canada. They had stations in the States. We augmented the number of sondes for a short period. You can't afford to fly sondes every day at all these stations. Nobody will give you enough money for that. But if you can do it for a couple of weeks, you can study processes. And so we had this independent network that had its own scientific goals apart from supporting the aircraft program. Because all NASA wanted us to do was to fly a few sondes so they could check their profile instruments. But we wanted to do more. And she coined this idea of strategic sounding networks, and it's been very beneficial. And in a way, the MATCH project is an example of it. This was started in Europe. The idea here was to try and deal with this, we're jumping back to the stratosphere here, but they try and deal with the fact that the Arctic vortex is very disturbed by planetary waves. Unlike the Antarctic vortex, which tends to be roughly round and stay in the same place, and you can just observe it statically and understand what's going on. The Arctic vortex moves around, splits up, wanders over Europe, wanders back over Canada, and that's all because of the large planetary waves in the northern hemisphere, because that's where all the land is. So they came up with this idea of using trajectory prediction, using a weather model to forecast where an air parcel was going to go over the next few days. And weather models are pretty good at that. And then they could sample by launching a sonde whenever it was this air parcel was going to pass over a particular station. So you have an initial sonde when, and then you follow that air parcel, and when that air parcel passes over another station in the global network, you send a message to them and say, can you launch a sonde at this time? And so all the stations in the world were coordinated, and their first paper in 1990, way back, 1990s, I think. Anyway, it was absolutely, there's this brilliant graph where they show the depletion if you measure at certain static places, and then if you follow the trajectory of an air parcel. And the first graph is just all over the place, and the second one, everything lines up on a straight line. The depletion is absolutely a function of time spent in sunlight and of the polar stratospheric cloud affected air. And so that's been going on for about 30 years. We also use similar methods to try and understand the influence of forest fires. There's a lot of ambiguous evidence about whether boreal fires produce ozone. And so what we did was we separated trajectories. We ran a lot of back trajectories from ozone sonde profiles and separated them according to whether they passed over forest fires, as identified by satellite measurements, and those that didn't. So we had a bunch of background profiles, or of background parcels at each height that were non-fire affected, and we had ones that were presumably fire affected. They apparently had passed at least close to a fire spot. And that worked extremely well. We have a nice paper on that. And there's more work to do on that if anybody's interested. And this is something that this is actually very recent work by a PhD student here in Jane Liu's group that I'm helping supervise. And this is absolutely brilliant. He's taken back trajectories for all of the ozone measurements in the World Ozone Data Center. And with back trajectories and forward trajectories, because ozone is relatively long-lived, you can say, if I have an air parcel, if I measure the ozone in this air parcel, and I know that that air parcel is over Winnipeg tomorrow, well, it's probably got the same amount of ozone in it. So you can fill in the spatial domain. So from 60 measurement sites, we get a global maps, which compared with other methods turn out to be extremely accurate. If actually in this paper, he shows it's in many regions of the atmosphere, it's better than MLS, which is the gold standard for satellite instruments. We've also done that with aircraft data that I mentioned. The mosaic data, although we just started in Canada, mosaic data has been available since 1994. And you don't get quite a global picture because they don't fly to Antarctica, unlike the sondes. But it's also fills in the spatial domain quite neatly. And it turns out that carbon monoxide is also fairly long-lived, and so those carbon monoxide measurements can be turned into global maps. And they compare very well with Moppet. Not entirely perfect agreement, slightly different trends. We got into some arguments with the Moppet validation team about that. And we've also done it with ACE. I mentioned you only get 30 profiles a day from ACE. Well, you can use this same method to move information around in the stratosphere. And in the stratosphere, the lifetime is of the order of weeks, not days. And then finally, I'd like to point out that fairly recent development, many weather centers, including Environment Canada, are now assimilating satellite measurements of ozone. And I think the jury's still out about whether it improves the weather forecast. But as ozone scientists, we think it's pretty darn cool. And so I've got here a comparison. The one on the left is the forecast. It's an 11-day forecast. And then on the right, it's the actual measurements. And you can see the correspondence is quite good. So just to finish up, some questions for us to think about, or for you to think about, because I'm pretty much done with this business. And yeah, I'll leave it there.
Right.
Microphone so that people watching online can hear you.
I have a few questions, actually. My first one was the last one on your slide there of,
New
are there any
sensors,
new
yeah.
sensors that you know of in development or improvements?
Actually, I know of a lot of them, but they seem to come and go. I've reviewed proposals over the years and then never heard anything more. There was a sensor that was being produced by the University of New Hampshire that was using a photocell and I think a UV sensitive photocell and some kind of I think a blue or UV LED, something like that. Anyway, I don't know what happened to it. It sounded really good, but I never saw any data from it. Or the trouble is, ozone sondes are relatively cheap, so you need to produce something that you can afford to throw away. I think there's a possibility for some of the small spectrometers, like the spectrometer that's in the Pandora, you can buy for a couple of $1,000. That's not that much more. It's about 10 times as much as an ozone sonde, maybe 200 now. We used to get them for 200. They're more like 400 now. So 5 times as much as an ozone sonde. So if you could recover them most of the time, you could consider flying them on a balloon and get an awful lot more information about the troposphere.
Yeah, I'm going to abuse my position because I do actually have a question. You mentioned that the IAGOS data was woefully underexplored. If someone here would like to take on that burden, have
Please
a little
talk
look.
to me. Yeah,
Just
I'll direct you in the right place.
Okay.
You don't need me. It's publicly available. But
Okay. Do you know where? Is it like online or do you just have
yeah,
to
but I
do some
can't quote the URL off the top of my head.
Okay.
So send me an email. I'll be happy
Okay.
to direct you to it and introduce you to the principal investigators and so on.
Is there any
So David, can you comment on the future of the brewer network? I think they're no longer being commercially made, is that right?
I hadn't heard.
Okay.
I don't know. I mean, if I were setting up a network now, I don't know what I'd buy. I don't think I'd buy a brewer. A very sensitive. It's a very sensitive instrument. It is the triad is really the global standard, and the double brewer is a very precise instrument, but it requires a fair bit of maintenance. They cost $500,000. You can get a pretty good measurement from Pandora. Now, I understand my colleague Jonathan is pretty scathing about the construction quality, but they're like $40,000 or something. And I mean, you can make a diode array spectrometer that'll give you more than just what the brewer does in a lot less expensively. So, no, I can't. So that's a long way of saying I can't comment really, but I'm not sure that they're the future. Another one? Should ask Tom. I'm sure he'd give you quite a different answer.
David, when we first started using Ozone Sound data to evaluate our data simulation products, I was given the impression that we should be cautious in our use of the Ozone Sound data to validate the near surface component of our simulation because of potential larger uncertainties associated with things like the ascent rate and so forth. But you showed a figure of the various uncertainties, and it didn't look as though the uncertainties were that much larger near the surface. So do you think we should actually use the SON data near the surface?
Yeah, I have. Yeah, I don't. There can be issues. There are some profiles where you see a very sharp change at the surface, and I have to suspect that the weather was lousy or something, and so they didn't go out and hold it for 10 minutes like they're supposed to before letting it go. They went, you know, it's miserable out here. Let the darn thing go. On the other hand, you can also have very sharp layers in the lower boundary layer that make large differences. In fact, our Eureka profiles always used to be low in the boundary layer because they were launched, I think, at 5 a.m. or something. So you had losses in the nighttime, surface losses at the nighttime, which weren't reflected in losses further up because there wasn't a whole lot of mixing. So you would have a sharp increase. But yeah, you sometimes you have to worry about contamination or bad procedures at the very bottom, but not very often.
So is there something that we could look at to filter out those particular profiles so that we can use more of the near surface data?
Just an algorithm to alert you to them, and you can look at them and see if you can see no physical reason. Maybe you want to put a caveat on that. But unfortunately, if the operators have screwed up, they don't usually note it in the logbook. And but generally they're very conscientious, very careful, very dedicated. So I'm probably doing them quite a disservice to suggest that even ever happens. And it's more likely to be just an atmospheric anomaly.
Okay, thanks.
Yeah, I've used the surface data a lot from ozone sots.
Just wondering if we have any questions online. No. Okay.
Thanks. I was wondering, yesterday you mentioned that there are situations, conditions where we might not be able to go out and measure, so maybe a thunderstorm. And here today you mentioned forest fires, that we have, some opportunity to sample them kind of by chance from the aircraft. Are there any other like extreme weather kind of phenomena that we aren't sampling very well that might be interesting?
Hurricanes, probably. No, there are sampling issues. I mean, at one point I wanted to look at how could we see a signature in our historical record from thunderstorms, some thunderstorm production of ozone. And so I mentioned this to my colleague Jonathan, who runs our network, and he laughed. He said, "You're not going to find any data. Nobody launches a sonde in a thunderstorm. They don't want to get hit by lightning." Oh, yeah, I suppose you're right. So I dropped that idea. But there are often things that you can find in the well, I've made a career out of looking at our long data record and finding interesting things. There's In the European record, you can find measurements of sulfur dioxide effectively in the ozone sonde record. There's whole periods where the Payern sondes were showing 0 ozone at the surface. And they happen to match up quite nicely with what the sulfur dioxide monitor was showing. So they weren't actually measuring 0 ozone. The sulfur dioxide was killing the measurement, which it interferes with the potassium iodide. Same thing happens if you're trying to measure ozone in a volcano. I attended a talk once where this postdoc, I think, had the fairly young fellow was showing us these lovely data, and this big notch in the as his sonde flew through the volcanic plume, and he said, so something in the volcanic plume is actually destroying ozone. And I was nice. I went up privately afterward and I said, actually, that's evidence that there's sulfur dioxide in the plume and it's killing your measurement. It's not affecting the ozone. So not everybody knows that. So.
Hi there, thanks for the talk. I'm wondering, typically, how far do your ozone sondes travel horizontally before the balloon pops? And is there any use or utility in trying to develop a sonde which is self-returning, so a more expensive sensor could be used or a higher precision measurement could be made?
I think there's fantastic opportunity for that. And I did look into drone technology a little bit in a few years ago. At that time, they were expensive, and I think still you need a pilot's license to operate them, plus extra training. So that made it a rather difficult program to run. But yeah, but I wouldn't put an ozone sonde. I'd put a spectrometer, a small spectrometer on a drone. And then you fly it around and fly it back to base and do it all again as often as you like. Now, of course, with the military interest in drones, drone technology has been changing rapidly. So I would imagine what I found a few years ago is completely obsolete, and there's a lot of possibility for drones. There are also directed balloons. They're super pressure balloons that can control their height by pumping gas in and out of the balloon. That's another possibility, and some of those are available commercially.
We have time for one more short question, if that's possible, but if not, I've already moved over. I anticipated the other side of the hall would be more questions.
Yeah, so my second question was, you mentioned a little bit your work going back in the data record and kind of looking at stuff from the past and reevaluating. I was wondering if there was any major conclusions or results from the past that you've reevaluated and it turns out not to be true, or that things have changed based on reevaluating that data.
Well, one of the things we discovered was that the Brewer mass sondes had, which we used in Canada until 1980, the older type, were quite less sensitive in the troposphere than the ECC sondes. They tended to have larger losses. And as a result, some of the big increases that we're seeing in the troposphere in the 1970s are probably instrument-based. And of course, I showed some plots from ozone sondes in the 70s in the talk yesterday, and that led to the idea that tropospheric ozone was increasing rapidly. That was mostly an instrumental effect. All of Bozkov's results can be shown to be, at least as the sonde plot that I showed that came from Bozkov's 1984 QS paper.
Okay, and if that's everything, we'll thank David one more time. And as a reminder, there is a pub night tonight at 6 p.m. in Prenup, and food and drinks, everything is paid for, so you can come buy whatever you want within reason.
Free drinks for graduate students? Mm. And professors. Wow, that's scary.